design of steel laminated elastomeric bearing with sole plates. Um, I hope you guys will enjoy this a presentation of mine. Um, the primary role of the bridge bearing um, is to transfer the load from the superstructure to substructure um, and allow the control moments. So in the introduction here, you can see even the pictures, the figures of the elastomeric bearing. Why am I talking about elastomeric bearing only is because we use this type of elastomeric bearing for our bearing design for all three bridges. The all three bridges means the first one is A301 to A306, second one is A313 to A314, and the third one is A341 to A3 B301. Oh yeah, I guess so. Yeah, B303. Yeah. Yeah, you will see. So the other types are pod bearing, spherical bearing, disc bearing, sliding bearing, rocker and roller bearing, SLMR bearing. Actually, these are under these bearings. So why it is in red? Because we don't need this right now. We are not designing this. So let's focus on the elastomeric bearing, and let's watch what's happening over here. So here it's showing a video of a bearing. Um, So it will go inside. That is pedestal, the one that you can see on the bottom. Concrete pedestal on the top, masonry plate. This is not a elastomeric bearing. It's a pot bearing actually, but just to show you a picture or a general understanding of the bearing, this is a video for you guys. So the next slide. So elastomeric bearing and HLMR bearing. HLMR bearing is also here because you will hear this type of bearing a lot while working here. So the image on the left shows rubber with internal steel reinforcement commonly used in bridge and structural application. These are cost effective, maintenance free, allow for vertical load compression as well as horizontal rotation and shear. So these are the reason why we are using it, because see, it's cost effective, maintenance free, so many things. So that's why we are using it. But sometimes we use HLMR bearing such as a pot style, disc style bearings. It's designed for high load conditions. So high load conditions. So why? Because it is used for heavy and complex structure. We are not using this. Um, so fixed and expansion bearing. So a lot of times you can hear that this term fixed and expansion bearing. So here you can see the example, what is meant by expansion and what is meant by fixed bearing. So you can see from the picture itself the difference between the expansion and fixed bearing. So the fixed bearing, you can see there is a pin, anchor pin on the bottom that fixes it on in place at one end on the bottom. So we calculate for the diameter for that bearing as well. And on the top, okay, yeah, bye. Um, on the top, you can see the expansion bearing. It does not have that pin. So that is a clear difference between the fixed and expansion bearing. Here you can see the bridge installation process. See, you can see the pedestal, you can see the masonry plate on the top, you can see the anchor pin, and you can see the workers doing their job by carefully installing the uh, bearings. And you can see the elastomeric bearing they are using. Usually they use neoprene or natural rubber for that expansion bearing. So we can go to the other side. So there are few design assumptions that we use. So the design assumptions are bearing for straight steel or concrete multi-beam bridges. So like the three bridges that we use are like they're straight breezes. They're not curved. So that's the first assumption that we use, that uh, they are for straight breezes. Usually breeze in curved or skewed breezes require more complex analysis. Um, Usually torsion, rotational in multiple direction, but here they are simplifying the design to a straight multi-beam breezes. So another assumption is we are using the elastomer hardness as 50 durometer SOAR A. That is like we usually we took these all from the reference standard you can see on the bottom, NYSGOT breeze manual, breeze design specification. So we use the SOAR A durometer. Uh, so what does that mean? I mean, the what is SOAR A, the durometer? It is the hardness of the elastomer actually. So the value of 50 SOAR A means that the elastomer is of medium hardness. So like there are different values for the hardness of durometer. There can be, for example, a durometer the durometer can be of 40, and it means that it is more softer elastomer and with more flexibility, and harder elastomer means it has a value of 60 or 70 or above and carries higher loads but allow less movement. So yeah, method A is used. There are like two procedure. We use there are like two procedure, but we are using procedure A in this bearing design. This is coming from the code, and I kept a screenshot on the right side from the code itself, from the LRF bridge design specification, coming from the BM 12.2.1. So you can see you can how procedure A can be done. What does that mean? Is written over there is the historic method that has been used for bridge design. You can read for yourself. I don't want to take a lot of time of your you guys. That's why I will just try to keep it short and simple. So let's go to another slide. Starting, we need to put some inputs in the for the bearing design. So for the inputs, we are using live load, dead load. Uh, uh, DW means the future bearing surface utilities, seismic load at fixed bearing. So for all the three breezes, I only used the live load, which governs the traffic loading on bearings, and the DC one, which is the non-composite. You can see for yourself, it's a self-weight of girder and fresh deck concrete, and we are not assuming anything for DC2, which is the permanent load after the slab hardens. I think we use that for splice design as well, but we are not using here. And future weighting surface, we are not using. Our inputs are like that, and then vertical curve data, we don't have a curve, we have a straight breeze, so 0 0. So bearing location, so station of center line of bearing lines. So this one we took from the structure profile. You can see all the chains on the structure profile on DP205 drawing on those GP sheets. We took it from here actually, there actually. So this is just the example on the bottom. You can see station of center line of bearing lines. All those values are from that particular sheet. So I took it from the chains and then added and then written it over there. This is just an example. The seven, I think I took it from uh, third or the maybe first one. I don't remember, but yeah, that's the point. We took for each and every chain is um, for example, the 580.146 is for the A3 O1, and then A3 O2, and then A3 O3. One is on from for the north, and one is for the south, because in expansion there are like joints on the middle. So in expansion we have to find the bearing dimension for both the size, because there will be two pairs. So we are calculating for both of them. So one is on the north, one is on the south, and then blah blah blah, and then we calculate the whole thing all station, and then location of fixed bearing, 0 is expansion, fixed. So what is starting with 0, expansion, then fixed, expansion, expansion, fixed. You can see from 1 and 0. And then is bearing line at an abutment? What is meant by that? Bearing line at an abutment, you can see from the picture. If it's on the abutment, usually it's usually on the end. So you can see one on the end, and then yeah. So is bearing line at the deck joint? 0. So this is all from the picture, from the structural profile. No joint, 0. Deck joint, there is a joint, write 1. If there is no joint, just write 0. So let's go to the other. So we have to this give the more material properties for everything. What is there? Girder. What is there? Elastomer, steel laminates, sole masonry plate, thermal expense. Everything we have to put, and they are all coming from the code itself. LRFD, the code, where is it coming from? 14.7. Usually 14.7 is the specs, guys. So elastomer. So I don't want to take more of your time on this material thing. So these are the tensile strength. um, so the first girder, fu, means the girder ultimate tensile strength. We took it as 70 ksi. This is the general material property that we took for all the three breezes. Then bearing analysis. So we take the elastomer dimension, length, width, and number of layers. This is the thing that we are designing. We initially just pick up a number, like let's say we will just like assume, okay, let's start with 14 and 12, and then let's see if it's it will pass the design check or not. And then like we will see for ourselves, like let's take 12 and 10. But what does the upper thing say on the top right? Specify the dimension for the elastomer to be analyzed. Note that the length should be less than or equal to width. So our length cannot be 12, and then width cannot be 10, because length is higher than the width. So we have to have length that is less than the width. So the length can be, we can test from length as 10 and then width to be 12. And then only we can get the K ratio that we would need to see, check later while doing the bearing analysis. Only then the K ratio will be a 1. So 1 is pass, 0 is fail. So I think the formula is like L by log. So that is how we do it. Uh, strength 1, total load calculated. So strength, that is also from the code. They took the factor by 1.25 did load. DW, we didn't take any live load. Is that distance to fixed bearing, expansion or contraction moment, and then we took design moment. The reason we took the design moment is to do the necessary check later. So we have to check for the deformation, shear deformation. So if we calculate the del T design, we can calculate the uh, uh, safe factor, and ultimately we can find the aspect ratio just to check if it's passing or not. So that's that. Deflection and stability, these are all the deflection checks we do. Differential deflection less is should be less than equals to 0.125. Total pad thickness versus allowable limit. Stability confirmed. So yeah, we do the check, and then we if it's under the limits, then it's confirmed, it's satisfied, and then yeah. So this is the main thing. We do so many checks here. Shear deformation check that I told you before, finding the design moment, and then uh, finding the deformation check one. Second is aspect ratio check. There are like various, so many formulas that we have, and then we need to uh, inquire that. We need to put that inside all those formula. Uh, okay, and then safe factor limit check. Uh, uh, Check number 4 is maximum compressive stress, and then the minimum compressive stress. So maximum and minimum compressive stress should like, that is the tricky part. Like while putting the dimension for the elastomers, if you put correct dimension, then the design will pass. Otherwise it's very hard to uh, like satisfy those uh, stresses. Like it's very hard. So like check 3 4 5 is like very important checks for us um, to satisfy the design. Then compressive deflection length, differential deflection, bearing stability, fatigue. So on the bottom you can see that if there is number 1, then it all passed, 0 is failed. So okay, sole plate design. So so you can see sole plate in the beginning of the video. There was sole plate on the top side, and there was masonry plate on the bottom. So we are calculating for the sole plate as well, length and width from the girder flange, width and elastomer size. Depends upon that. This is all we need to calculate. It will calculate from the length and width of the elastomer that we gave and that we provided on the in the beginning. So I think the formula is like we just add 1, and then it will calculate. Minimum thickness is 1.5 inch. Bevel required if grade bevel is required if grade is greater than 1%, or DLT is greater than 0.125 inch. So in most of our check, in all the checks, we don't require the bevel. So that was the result. I have not kept the result for all 3 bridges, just to make it short and simple. So let's go to the other slide. Oh, 1 minute. Let's go to the other slide. Bearing anchorage and restraint loads considered are from temperature, braking force, wind loads. These are the things that we calculated. We also have the wind load on vehicles. We took the wind load at 0.1 k per f, and we calculated the f horizontal pin factored for this. For this, we calculated the force, horizontal force for force with different combination. These are all the combinations: strength 1, strength 3, strength 5, and then the service 1 and extreme event, and then we took the maximum of all. These are all required to find the like while calculating the moment and ultimate shear at base of pin. We require this. um, so because there is a check for the moment and shear as well. Fixed bearing anchor pin design the anchor. This is the anchor pin that I showed you on the beginning of the slide. We had the anchor pin for the fixed bearing, and that's the top part of it, which is zoomed in. That's the detail. You can see the sole plate here and the anchor pin, center of the anchor pin, and then we have to calculate the phi p as well, which is the dimension of the pin, design anchor pin to resist the moment and shear at the base of the pin. And that's the objective of this design. Ensure pin diameter is adequate under combined flexure and shear condition. And then the check that we do for this is that the P pin should be less than 3 inch. The difficulty that I faced while calculating or finding the reason for everything while doing the bearing design is that my FP was usually more than 3, and that's why I had to check everything, make sure the formulas are correct, make sure they are like the template that we had is correctly done. So yeah, some of the things that I had to fix, and yeah, we were able to achieve 15 that is less than 3 inch. So let's go to the other slide, which is the masonry plate design. Yeah, we designed the sole plate, so of course we have to design the masonry plate as well. So this is just a table that I took from my design. So that is for different locations of piers. You can see WM width. So you can see in the picture as well. This is the width and the length. We calculate the thickness. We calculated the ET, which is the minimum is distance, minimum longitudinal is distance, uh, and then EZ, and EL, the transverse and rotational, I guess, distance, and then VM. Um, we calculated that as well. Let's go to the other. Yeah. So this is the final design summary. Elastomer dimension, we calculated the length, width, and the number of layers. We calculated the sole plate thickness, the steel sole plate, and the masonry plate dimension and the thickness. So, and then we found out that all the checks, all the AASHTO or NYS DOT checks are satisfied. So you can see on the picture, um, uh, like this is for the fixed elastomeric bearing. This table is for only that. Um, I was not able to show the other one, uh, just to keep it short and simple again. We use four number of quantities. We use these are the inputs, the dead load and live load. These are the other things that we calculated. These are the inputs, and these are the calculation that we did. Um, and then yes, we found the fee pin less than 3. So this is yet to be updated. So yes. Conclusion: the designed steel laminate elastomeric bearing fix and expansion with sole plate satisfy all the LRFT design checks: stress, deflection, fatigue, stability, and serviceability. Bearing dimensions are within the standard limits, and sole plate design meets strength and thickness requirement. There is no issue with thermal or wind-induced movement. The design is acceptable for use in steel, straight steel multi-girder bridge with urban wind conditions. So to conclude the steel laminated elastomeric bearing with sole plates designed for this project successfully meet all the LRFD and NYSDOT requirements. So, yeah, like there were no issue with thermal, wind, or load-induced moments. The chosen dimension and material properties fall under these standard limits. The bearing satisfy the strengths, stability checks. So we are all good in that. So in this presentation, we walked through the different types of bearing used in the bridges, the design assumption and the standard followed, the load consideration, and material properties. We also went through the detailed bearing design process, including the analysis, code check, and anchorage. So yeah, this is the conclusion. And if you have any questions, anything, just let me know. I will try my best to answer all of your questions. Thank you.